let's talk about how we've been doing things and what some of the vulnerabilities are. So this diagram shows two parties who want to communicate. In this case, they're connected with a fiber you see at the top there. They could also be connected by some free space method, for example, a satellite. It doesn't change the way they communicate, which is by using bits and encrypting those bits. So Alice applies a secret key to a string of bits and encrypts them, and Bob has the same key and can decrypt them. Now, one issue with this method of communication is the math algorithm that you use to do the encryption. All math algorithms are subject to being broken or cracked. There's a lot of motivation to do it, both from nation states as well as from those with other types of bad actors who want to steal the information for economic reasons, perhaps. But you're using math, which means it can be broken. The other issue with this classical network here of bits is bits can be copied. It's actually fairly trivial to latch on to the fiber in this case and copy the bits. And once the bits are copied, they can be decrypted. If not today, they could be decrypted at some point in the future. And that attack is called harvest now, decrypt later. You copy the bits now, you save them until you have maybe a powerful enough quantum computer with enough qubits to break the RSA encryption, or some other method of breaking it, maybe using all the advanced AI and supercomputers that are available today or in the near future. So what we're going to talk about today is a different way to secure communications between parties, a way that doesn't use math at all. It uses physics, and so there is no algorithm to crack or to break. It's physics, specifically entanglement, that is securing the information. There's no exposure of your key at any time on the network in public, which is what happens today with public key cryptography. So let's look at the same diagram. And now Alice and Bob, they still have a fiber between them, the same telecom fiber that we've been using, for decades. But now, instead of bits traveling down the fiber in the form of laser pulses, we've got pairs of entangled photons that are emanating from another laser, a different type of laser. But the entangled photons, one goes to Alice, one goes to Bob. And by measuring those photons and by verifying through software that they are entangled, because not every pair is entangled, then Alice and Bob can build up a shared secret, a string of bits that is truly random and that is only known to them because they're the only ones who could have measured those entangled photons. So this is called physics-based security, as opposed to what we saw on the other version of this diagram, which was math-based security. And it's very important to understand that none of this key material was ever sent down the fiber or sent down from a satellite in that case. It was derived by both parties at the same time using this principle of physics, principle of nature called entanglement. In addition to being uncrackable because there's no math to break, another very important benefit you get from an entanglement-based secure network is that eavesdropping becomes impossible. There's no way to copy these photons. These photons are qubits, basically, and you can't copy qubits. When you measure the qubit, which Alice and Bob will do, they collapse to a classical bit, either a 1 or a 0. And therefore, that means that if Eve, the eavesdropper, grabs some of these photons as they're traveling down the fiber and measures them, those qubits will collapse. And what will happen is Alice and Bob will see their error rate go up. And if they have a good software solution, software stack in place to run this network, it will alert them that there is an eavesdropper on the line, and they can take a countermeasure. For example, switching to a different path, a different channel. So not only do you have physics-based security with no chance of mathematically breaking it, but you have eavesdropper detection and protection, which you don't get on a classical network. As we discussed, on a classical network, anyone can tap your undersea cable or whatever it is and copy all the bits as many times as they want.